This video is over lesson 78, products of square roots, and is for my pre-algebra classes. So ladies and gentlemen, this lesson starts off with this property right here, which we're going to be really focusing on and using throughout. So the square root of a times b equals the square root of a times the square root of b. So the idea here is that when we are multiplying two things together, the root can distribute to each of these, so it can split. Which means that anytime we have the square root of something, so for example square root of 12, we can reimagine this. And so if I reimagine this, so imagine 12 as two numbers being multiplied together. So 1 times 12 might be the easiest. So then I can split this up to the square root of 1 times the square root of 12. Likewise, if I can imagine it as some other product, like 2 times 6, I can split this up into the square root of 2 times the square root of 6. As a third option, we could also imagine 12 as 3 times 4. And so this would be the square root of 3 times the square root of 4. So these are all true statements. Now let's take a look at them and see if any of these are particularly useful. So for this first one here, the square root of 1 is 1. And then the square root of 12, well, this is the square root of 12. And we would say this as 1 square root of 12, which of course 1 times anything is just itself. So really this just leads us back to the square root of 12 is the square root of 12. While true, not terribly helpful. We would have known that without having to do any of this. So while true, not particularly helpful. Over here, the square root of 2 is irrational. The square root of 6 is also irrational. So again, while true, this doesn't really do too much for me at this moment. Now there might come a time later on where maybe we're in a fraction and there's a square root of 2 on the bottom. And so then my square root of 2 on top could reduce with my square root of 2 on bottom. Maybe. But that's not the case we're in right now. Over here, the square root of 12 equals the square root of 3 times the square root of 4. Well, the square root of 4 is 2. Now notice here, ladies and gentlemen, that the multiplication has been implied, but when we have a number behind the radical, we have to write in the dot. We can no longer imply it. Also notice that I make sure that my radical bar does not go over that, otherwise they would both be inside the radical again. Okay, so a couple things to watch out for there. I'm going to flip this around to the front, because if I flip this around to the front, then the multiplication can be implied, and now I have what we would say here is 2 square roots of 3. Well, that might actually be somewhat helpful. So ladies and gentlemen, what we've stepped upon here, looking at this property, is a thing that I like to call reducing radicals. So remember that a radical is just the square root symbol. So reducing radicals. So what we just did here, we're going to do it one more time. Square root of 12. But this time I'm going to put my square root of 4 first, because then I can do less writing. If I put my square root of 4 first, I know square root of 4 is going to have a nice answer, 2. And now there's nothing that needs to be flipped around. So the square root of 12 is actually 2 square roots of 3. So ladies and gentlemen, the idea behind reducing radicals is we want to take our radicand, our number inside the radical, and we want to, in our minds, split it apart into something times something, where one of those somethings has a nice square root. Well, if one of those somethings has a nice square root, that means it is a perfect square. So we use perfect squares to help us simplify and reduce our radicals. So if we go through our perfect squares, the first perfect square is 1 squared, which is 1. That's not going to be terribly helpful. We saw what happened up here. Just like in a fraction, if you reduce the numerator and denominator by 1, nothing happens. Here, if we choose 1, nothing happens. So we're going to skip that one. So the second perfect square, 2 squared, is 4. The third one, 3 squared is 9. The fourth one, 4 squared is 16. The fifth one, 5 squared is 25. Then 36, 49, 81. Oh, sorry, 64, then 81. I always want to forget 8 for some reason when I do this. And we'll go one more. 10 squared is 100. So ladies and gentlemen, you want to have this list in your mind. You want to have 4, 9, 16, 25, 36, 49, 64, 81, and 100 in your mind when it comes to reducing radicals. Because we're considering, can we split our number up into something times something where we could then simplify. So if we take a look at a few more examples, let's start with the square root of 75. So can I split this up into something times something where one of these perfect squares is one of these somethings? Well, sure. 25 goes into 75 3 times. And of course, the square root of 25 is 5. So 5 square roots of 3. We take a look at square root of 48. It's their perfect square that goes in there. And you probably have one in mind right off the bat. 4, of course. 4, and that'll be then times 12. So the square root of 4 is 2. So this is 2 square roots of 12. However, ladies and gentlemen, just like reducing fractions, when it comes to reducing radicals, we have to consider, is it completely reduced? Can we reduce it more? So just because I've reduced doesn't necessarily mean I'm done. I have to consider, is there another perfect square that I can pull out of this number here, this radicand? And of course, with the 12, we can pull out another 4. So this will become 2 square roots of 4 times the square root of 3, because 4 times 3 is 12. So now I've got my 2, that was outside, times my 2, that is the square root of 4, and then, well, square root of 3 is just stuck. Last step, finish this off. 2 times 2 is 4, so this is 4 square roots of 3. However, speaking of fractions, just like with fractions, if you can find a larger number to reduce by, then you reduce more quickly. So we're going to go back and do this one more time. And is there a larger perfect square that goes into 48? And I'm sure some of you right now are saying 16. 16 times 3 is 48. Square root of 16 is 4. So by choosing a larger perfect square, you can see how much shorter my work is. So I highly recommend, ladies and gentlemen, that you really take a look when you're reducing radicals at, do you have the largest perfect square before you start doing your work? Now, of course, if you're stumped and you've found one and it works, well, go for it. And sometimes it's just going to take longer. But if you can find that bigger one, it will save you time. All right, we're going to do just one more easy one here real quick. Let's say we have the square root of 200. Now, of course, that is 100 times 2, and the square root of 100 is just a plain old 10. So 10 square roots of 2. And that is reducing our radicals. So we're going to move on now to what the title actually is implying here, and that is products of, and I'm going to write radicals just because it's shorter than square roots. So now let's take a look at what happens when we multiply these. Well, ladies and gentlemen, basically what's going to happen is we're going to be taking this property up here, and whereas reducing has us start with this and move to that, multiplying square roots is going to have us go from here back to there. So for example, if I have the square root of 2 times the square root of 3, and no, I don't technically need the dot there. It could be implied. I just put it there to emphasize that we're multiplying. Well, like the property says here, well, 2 times 3 is going to be its product, whatever that is. So 2 times 3 is 6. So the square root of 2 times the square root of 3 actually is the square root of 6. If we move on here, let's take a look now at the square root of 10 times the square root of 2. So square root of 10 times square root of 2, well, 2 times 10 is 20. Now, ladies and gentlemen, if you circle your answer right there, unfortunately, you are going to get your answer wrong, because as we're doing these, we have to consider what we learned up here. Can we reduce this radical? So is there a perfect square that we can pull out of 20? And of course there is, because 20 is 4 times 5. The square root of 4 is 2, and well, square root of 5 is irrational, so it's just stuck. So that's 2 square roots of 5. Let's take this up a little bit of a level now. Let's say we have a mix of things inside and outside of the radical. So for example, 2 square roots of 2 times 3 square roots of 2. Well, ladies and gentlemen, this is actually quite simple. All we're going to do here is we're going to multiply the outside stuff with the outside stuff and the inside stuff with the inside stuff. So on the outside, we will have 2 times 3 is 6. And on the inside, we'll have 2 times 2 is 4. Now we need to see if we can simplify. Well, of course we can. Square root of 4 actually comes out nicely. So this will be 6 times 2. And then 6 times 2, of course, is 12. Now this is important, ladies and gentlemen, for you to realize. 2 square roots of 2 is going to be an irrational number. This is an irrational number. 3 square roots of 2 is also an irrational number. So sometimes when we multiply an irrational number with an irrational number, we do actually get a rational number out. Let's do this one more time. This one is special in that we could have done it a little faster, actually. Of course, 2 times 3 is still 6. But remember that what a square root is asking is it's saying what times itself is 2. So this right here represents whatever number you would take to multiply by itself to get 2. So if you do multiply it with itself, the result should just be 2. So square root of 2 times square root of 2 would just be 2. Just like the square root of 3 times the square root of 3 would just be 3. So this would be an alternative way to solve this one, still giving us the answer of 12. All right, another example here. 4 square roots of 3 times 7 square roots of 6. Outside stuff, 4 times 7 is 28. Inside stuff, 3 times 6 is 18. Consider, can we reduce this? Yes, we can. So this would be 28 times the square root of 9, and then times the square root of 2. 9 times 2 is 18. Of course, then, this will be 28 times 3, and square root of 2. Well, 3 times 28 is 84, and the square root of 2 is still stuck there. So 84 square roots of 2 there. I'm going to show you another way that we could actually do this one, just a slightly different alternative. So noticing we have a square root of 3 here, and 6 is really 3 times 2. We could have split this up. Could have split this up before doing it. So I copy my problem down, but then I'm going to take my second number here and split it up into the square root of 3 and the square root of 2, because 3 times 2 is 6. So from here we're going to see we've got 4 times 7 is 28. Square root of 3 times square root of 3 would be just a plain old 3, but then, well, square root of 2 is just stuck, leading me to that same answer of 84 square roots of 2. So it doesn't matter which way you do it, two different options there. All right, let's take a look at another example here. 9 square roots of 10 times 11 square roots of 15. So again, outside stuff, 9 times 11 is 99. Inside stuff, 10 times 15 is 150. So this is 99 square roots of 150. Well, is there a perfect square that we can pull out of 150? So if you're not sure, actually go through your list. Does 4 go into 150? Does 9? Does 16? Does 25? Ooh, 25 does. Think about quarters, right? So if we think about quarters, this would be 99 times the square root of 25, and then how many quarters are in a buck 50? 6 quarters. Finish it off. 99 times square root of 25 is just a plain old 5, and square root of 6 is stuck. Multiply those together, I get 495 square roots of 6. Likewise to what we did up here, we could do something similar with this guy. So we'll do him just one more time. So I notice there's a 5 in both 10 and 15. So what I could do is I could split this up into square root of 5 and square root of 2, because 5 times 2 is 10. And then for the other one, 11 times the square root of, well, that would be 5 square root of 5 and square root of 3. 5 times 3 is 15. So now if I put this all together, outside stuff, 9 times 11 is 99 still. So square root of 5 times square root of 5 will just become a plain old 5. And then square root of 2 times square root of 3, 2 times 3 is 6. Now 99 times 5, again, is 495 square roots of 6. So you'll notice in both of these examples that it might be just a little less writing doing it this way. However, doing it the first way might be conceptually a little easier. So it doesn't really matter which way you do it, just make sure that you do something that you're comfortable with, something that you're confident that you know how to do and that you can get correct. So we're going to go ahead and flip to the back now. And we are going to use our skills in a little problem here. So what I'd like you to do is move over here just a little bit, and we're going to make a coordinate plane on our papers. Wouldn't bother grabbing graph paper. We're not going to need a whole sheet of graph paper. So I want to go about 4 lines down, and then do your best to try to make it about as wide as it is tall. Don't forget your arrows on each end of your axes. Now we're not going to need a ton of space here. I want to go, let's see, we're just going to go 1, 2, 3. We're going to use the blue lines. 1, 2, 3. And then about the same distance. 1, 2, 3. 1, 2, 3. And now what we're going to do is we're going to put a rectangle on here. So I'm going to come over 1, 2, 3 spaces and go up 1. And then I'm going to go left 1 and down 1. And then we can connect those dots. Next, we're going to go left 2 and up 1. And then I can connect these dots. And then finally, we're going to go right 2, and then we're going to go up 3. Now, since we're doing this freehand, there might be a little bit of human error here, but it should be close. So you can see this is close to being a rectangle. This point looks a little off, so I might not have done it perfectly, but it's close enough that we can imagine. So here's my rectangle. So as I look at my rectangle, I have a length here, and I have a width here. So I need to know how long these are. On a coordinate plane, if we want to find a length like that, we can actually use the Pythagorean theorem. So if we imagine a right triangle connecting these two corners, then the hypotenuse would be the length of my rectangle. So, therefore, how long is this? Well, 1, 2, 3, 4, right there. Put that with my pen. And then this right here is 1, 2 units long. So Pythagorean theorem would tell me that 4 squared plus 2 squared equals, and I'm not going to say c squared because this is actually my length, so I'll say L squared instead. My c this time is L. And we solve it. Remember, first we simplify. We always simplify before solving. So 16 plus 4 equals L squared. I can simplify this more. 16 plus 4 is 20. And now take the square root of both sides. And I'm just going to flip this over now. So L equals the square root of 20. Now, of course, square root of 20 is the square root of 4 times the square root of 5. We can reduce that. And square root of 4 is just a plain old 2. So the length here is 2 square roots of 5. Now I want to find the width. So I'm going to imagine a right triangle right here. Let's actually put our right angle symbols in there just to emphasize that. So there it is. Down here, this is just one space over. So that's one space over. And then to go up, 1, 2 spaces up. So for my width, it's the same idea here. But this time I have 1 squared plus 2 squared equals my width squared. Simplify, 1 plus 4 equals w squared. 1 plus 4 is 5. Square root of both sides. Therefore, w equals the square root of 5. So, what is the area? Remember that area equals length times width. So therefore, A here equals my length, which is 2 square roots of 5, times my width, which is just square root of 5. And so if we solve that, outside I have a 2, and then an invisible 1 technically. We'll just leave it invisible. So 2 is outside. And then square root of 5 times square root of 5, of course, well, 5. Just plain old 5. Which means that the area of this rectangle is 10. And since we don't know the units, we're going to say square units. And that, ladies and gentlemen, is the end of our lesson.